Hi and welcome to Unit 1, Topic 3, Video 17. In this video we're going to look at Theorem 4, which is the theorem to do with cyclic quadrilaterals and supplementary angles. So Theorem 4 has a proof and the proof is above. As I mentioned in Video 16, to keep in mind this proof, let's go back and have a look at this proof. So you might want to pause now and have a look at it. In this proof we have shown that two opposite angles in a cyclic quadrilateral add to 180, and that's what this theorem says, that these two angles add up to be 180. So example 3 asks, calculate the value of m and n. Now the example 4 is there, which will be a subsequent video. So we'll do example 4 in later in this video, and we're going to work on example 3 now. Calculate the values of m and n. Well, I know this. I know that this value here is 180 minus m, and this value is 180 minus n. It's always good with these examples, and I'll start doing this more and more to track out how I'm going to do it. That relates to this, that's 50, and this relates to 180 minus 50. So I can track it that way, and I can do the same thing here. But now I'm going to write it out using mathematics. So the first thing I do is I denote my points, just the key ones, A, B, C, and D. You can do this on a diagram in the exam. You could put an E here if you want to, but I don't need the E. Now I'm going to make a note that angle DAB is equal to 180 minus angle DCB. So that is equal to 180 minus that. That means that n is equal to 180 minus, now angle DCB is 180 minus 130, because these are angles on a straight line. So I might make that note here, cyclic quadrilaterals, and here angles on a straight line. So I need to produce some evidence with each of my steps of proof. Now this is of course just simplifying, and I get 130. So n is equal to 130, and for a very similar reason I get angle CBA is equal to 180 minus angle CDA. This is also a Q again, cyclic quadrilateral. And so that gives me m is equal to 180 minus 120, which means that m is equal to 60 degrees. And this is, again, angles on a straight line. Okay, so that's example 3, calculating the value of m and n using the circle theorems that we know to be true already. Okay, let's look at example 4. So in example 4 is a little bit trickier. We're asked to determine whether two lines are parallel, but we have to determine the actual diagram first, which makes it trickier. In a lot of questions you'll be given a diagram. If two circles intersect at B and Q, so let's start with two circles intersecting at B and Q. Circle 1, circle 2, B and Q. Choose a point X such that it can be extended to meet circle 1 and circle 2 at two places. So I'm going to put X here, but I have to have a little bit of knowledge. You might find that you would sort of fail at this diagram a couple of times first. BX can be extended to circle 1. So this is circle 1, by the way, and this is circle 2. So if I extend BX, I get, now it meets circle 1 at A, and it meets circle 2 at C, and then QX, so this is Q, can be extended to meet circle 2 at R and circle 1 at P. So there's my diagram. I need to prove that AP is parallel to CR. Okay, now to do that I'm going to use angles in parallel lines, but I need to fashion up some information first. So here's another line, but BQ may not be parallel to AP and CR, I just don't know. what I'm going to do is I'm going to start with a theta up here, and I'm going to move that theta around. Now in planning, I can see that I can move that theta to here using cyclic quadrilaterals. Then I can move it to here using angles on a straight line. Then I can move it to here using cyclic quadrilaterals, and then I can move it to here using angles on a straight line. And I'm hoping that these two angles will be corresponding, i.e. equal, and therefore AP must be parallel to CR. So that's that converse of our earlier angle theorems. So let's have a look. I know that angle AP, sorry, that's wrong word to start with, PAB plus angle PQB has to be equal to 180 degrees. And this is a cyclic quadrilateral. And so therefore, angle PQB is equal to 180 degrees minus theta. And I know that angle BQR plus angle PQB is equal to 180. This is angles on a straight line. And so therefore, angle BQR is equal to 180 minus theta, which is equal to theta. And I know that angle BCR plus angle BQR is equal to 180. This is cyclic quadrilaterals. And therefore, angle BCR is equal to 180 minus theta. And I know that angle RCX plus angle BCR is equal to 180. And these are angles on a straight line. And therefore, angle RCX is equal to 180 minus theta, which is equal to theta. And that's equal to angle XAP, or I'm going to use BAP because that's what I used before, BAP, and therefore AC is parallel to CR due to corresponding angles. So, just to show you what I've done and use some colours, let's start with orange. I've started with this angle and this angle, and I've shown that they're opposite cyclic quadrilaterals, 180 minus theta. And in green, I've used this angle here and here to show that this is theta. And light blue, I've used this angle and this angle to show that this is 180 minus theta due to cyclic quadrilaterals. And then in purple, I've used this angle and this angle to show that this must be theta. And I've got theta and theta, and so I must have corresponding angles, and therefore they must be parallel. So that's the end of our work on corresponding angles. Hopefully you enjoyed example 4. You'll notice here that it's much easier to do once you've mapped out the way you're going to do that proof. All the best.